at point I, let's take a function y that is expressed as a product of 2x minus 1 times 3x minus 7. So we have a product, but I don't have a rule just yet to handle the derivative of a product, right? Because I told you, we look at these derivatives. When you try to evaluate the derivative, I'm not going to go and derivate whatever is in the first parenthesis, 2x, or each one by one. That's not going to be possible. You're going to be wrong to do that. When I'm trying to evaluate the derivative of a function, as I mentioned earlier, I need to look at this expression from the overall and evaluate the most important thing that happens here is a product of two expressions. I don't really care what expressions they are. The first thing that I see and I have there is a product. I would need to derivate this product and handle it accordingly, but I don't have a rule for that just yet. So at this point, I cannot approach this derivative by derivating each term in those parentheses separately, because that would be wrong. That would give us a wrong result. Instead, what we can do, as you've seen before, simplify or modify that expression into a form for which you actually have rules for differentiation. And in this case, we will learn how to differentiate a product. But for now, we are bound to only those 5 rules, which don't include the product rule. In other words, instead of starting differentiating this expression the way it is, we can simplify this expression first and then differentiate the expanded version of this function. So in order to expand this expression, I'm going to take each term and multiply it with every term in the next expression, just like you see here. And the result is going to be 6x squared minus 14x minus 3x plus 7. Let's add together all the like terms. So the expression can be simplified to 6x squared minus 17x plus 7. As you can see, this is a polynomial expression that we've encountered before, and although we use all the rules that we have, the constant rule, the power rule, the constant multiple rule, sum rule, and difference rule, we can very easily determine the derivative of this function. Let's differentiate. dy dx is going to be ddx of this expression 6x squared minus 17x plus 7, and that is going to be the derivative of the first term 6x squared minus the derivative of the second term 17x plus ddx of 7. And as we know, the first derivative is going to become 6 times the power, so 6 times 2, I can write directly 12, x at power 2 minus 1, which is 1. I don't write the power 1, right? So it's 12x minus the second derivative is going to be 17, the constant, times the derivative of x is 1. So minus 17. That's all it is. The last derivative of the constant 7, as we know, is 0. So we don't write that. And you see how simple calculating this derivative becomes. Let's try one more. Point J. Let's consider the function y equals to a quotient 9x at power 7 minus 15x at power 9 over 3x at power 5. Try to look at your expression. It's a quotient, and you know you don't have a rule to handle quotients directly just yet. Don't worry, we're gonna have one soon. I'm gonna give you a formula for that as well, but at this stage we can't really approach it directly. So the alternative is take this expression before trying to differentiate it, because again it's a quotient. So if I derivate this expression as it is, I have to derivate it as a quotient. I mean, that's the first thing that I have to approach. I don't care what is in the numerator or denominator. If I derivate, I have to derivate the quotient first, and then I take each expression in the numerator separately and denominator and see what methods I apply to derivate those expressions. So if you don't want to approach this function as it is, in this case It's not that we don't want to, but we can't handle a quotient because we don't have a formula for that. We don't have a rule to approach that just yet. Then the alternative is to simplify this expression before we try to differentiate. Like I did before, I can take the denominator and put it in the numerator as negative powers, and then we're going to have a product, and we can expand the product and so forth. But that sounds a little more complicated than it has to be, because what I notice here is that each of the terms in the numerator are multiples of the denominator. So if I separate this fraction into two smaller fractions, I can actually get rid of the denominator by simplifying some of those terms. Let's take this approach. I'm going to rewrite this fraction as two separate fractions. So I'm going to say 9x to the power 7 over 3x to the power 5 minus the second fraction would be 15x to the power 9 over 3x to the power 5. Now I can actually reduce 3 in the denominator with a 9 in the numerator. I'm going to be left with 3 over there. So what is left from the first fraction is 3 times x to the power 7 minus 5, because I'm bringing this x to the power 5 from denominator in the numerator as well. While in the second fraction, 3 from the denominator is reducing 15 in the numerator, leaving us with 5. The second fraction, we are left with 5 times x to the power 9 minus 5. The same rules applies here. And let's simplify this expression. It's going to be 3 times x to the power 2 minus 5x to the power 4. And I'm going to leave it like that because what I want to do is derivate this. And as a matter of fact, it's easier without having a factor because we don't know how to handle that products at this stage. So as a difference like that, two separate terms are actually quite easy to derivate. So let's derivate this expression now instead of the quotient that we had initially. We can write dy dx is going to be d dx of this expression 3x squared minus 5x to the power 4. As we know, as a difference, we can separate those derivatives into two smaller derivatives. In other words, d dx of 3x squared minus d dx of 5x to the power 4. And the first derivative becomes 6x minus the second derivative becomes 5 times 4, the power, right, is 20, x to the power 4 minus 1, which is 3. So 20x to the power 3. If you wish, you can factor out 2x, but the way it is right now, it's fine as well. And this is how you approach these kind of examples. Even when you don't have all the formulas that you need, you can simplify your expression and bring it to a form that you can handle with the rules that you already have. So hopefully this will help you differentiate any polynomial function, even if they include products or quotients, even though for those I'm going to give you the formulas in the next lessons. For now, thanks for watching.